In the last video, we learned about electronic configuration of elements along with spin configuration. Now we'll move a step further and do molecular configuration. So to determine the molecular configuration, we need to find out the total number of electrons in a molecule and then do the configuration as we do for the element. For example, if there is carbon monoxide, in carbon monoxide, there is a carbon atom and an oxygen atom. A carbon atom has 6 electrons and an oxygen atom has 8 electrons. So add them together, this gives us 14 electrons. So now we'll do the configuration of 14 electrons. That is 1s2, 2s2, 2p6, 3s2, and 3p2, 2, 4, 10, 12, 14. Similarly, for nitrogen, there are 2 nitrogen atoms and each nitrogen atom has 7 electrons. So 2 times 7, this is 14 electrons. So the configuration will again be 1s2, 2s2, 2p6, 3s2, and 3p2. Now we can see that both of these molecules have the same electronic configuration. So we can call these two isoelectronic configurations. Next is ionization energy. Ionization energy is represented by IE. It is measured in kilojoule per mole, and it is an endothermic process. So what happens in ionization energy? It is the energy required by 1 mole of a neutral gaseous atom to give a monopositive ion. This is the first ionization energy. So we have sodium in the gaseous state. And the sodium loses an electron. This is ionization energy 1. The second ionization energy is when a monopositive ion loses another electron. So for that, we'll take example of magnesium. So for example, magnesium in the gaseous state, it first loses 1 electron. So this is IE1. And then when this magnesium plus 1 ion loses another electron, this is IE2 and then onwards. Now E1, IE2, and IE3, these are called successive ionization energies. These are successive ionization energies, and going forward, the energy increases. This is because the proton to electron attraction increases. So if you draw a graph for the successive ionization energies, The x-axis has number of electrons, and the y-axis has the log of ionization energies, because ionization energies are too large to be written down. Now, what is happening over here is that over here, this is the first electron. Then here is the second electron. And then third, fourth. Over here, we have the 10th electron. And then this is the 12th electron. The first two electrons are being lost from the outermost shell. That is the 3s orbital, because the configuration of magnesium is 1s2, 2s2, 2p6, and then 3s2. The first two electrons are being lost from the 3s orbital, which is furthest away from the nucleus. So the attraction is least. So over here, the ionization energy is least. As we go forward from 3rd till 10th, the electrons are being lost from the second shell, that is 2p and 2s orbitals. That is why the energy increases. And then again, there is a large gap, after which we have 11 and 12, that is from the first shell, 1s orbital. And here this is closest to the nucleus, so it has maximum energy. This was the electronic configuration of magnesium, and this graph was for magnesium. Now, if, for example, there is a certain element X, and for that element, these are the ionization energies given in kilojoule per mole, and we have to determine that how many electrons are in its outermost shell and from which group does this element belong. So what we'll do is we'll see the difference in ionization energies. So the difference between the first two is 600. Next two have a difference of 1600, I think. And the last two have a difference of 800. So we have to see where there is the greatest gap, because as we saw in our graphs, when there is the largest gap, there is a change in shell. So over here, the largest gap is between IE2 and IE3. That is of 1600. So this means that the first two ionization energies are for the outermost shell. That means that the outermost shell has 2 electrons. And if the outermost shell has 2 electrons, that means that the element is from group 2. So 2 electrons in outermost shell and group number 2. Now, if for example, we had sodium in the solid state, so how would ionization and how would ionization take place over here? So over here, first sodium would be converted to sodium in the gaseous state. This process is called atomization. And it is endothermic. Also, in this process, the product is only 1 mole of a gaseous atom. And it has to be a gaseous atom. So for example, if we had fluorine and atomization takes place on it, so we would get only a fluorine atom and we would represent it as this. So if a sodium in its solid state is being converted to a sodium ion in the gaseous state with the removal of an electron, then over here, both atomization and ionization are taking place. Now, a question regarding ionization. So if we are given two equations, the first one is sodium in the gaseous state being converted to sodium ion plus electron, and sodium again in the gaseous state is being converted to sodium 2 plus ion plus 2 electrons. Now the energy required for the first reaction we represent by W. We're just representing it by W, it's not like a fact. And for the second, we're representing it by X. And we have to find IE2. So W represents IE1 and X represents IE1 plus IE2. So to find IE2, we need to subtract W from X, because X is the sum of IE1 and IE2 and W is IE1. So this will give us IE. This will give us IE2. X minus W will give us IE2. Next are the trends of ionization energy. So first is the group trend. Now in a group, for example, we take the first group of the periodic table. So we have first lithium, then sodium, and then potassium. So down a group, the atomic radius is increasing because there are more shells, more electrons, so more shells, so greater radius. So that is why in potassium, the outer electrons will be further away from the nucleus than in lithium, which is why the attraction of the nucleus to the outer electrons will be weaker. Now, to explain this further, we'll take the concept of screening electrons. In lithium, there are two shells, the first shell and then the 1s orbital and then 2s orbital. So over here, 1s orbital, the electron in 1s orbital are the screening electrons. In sodium, there are three shells. The first and second shell, the electrons in the first and second shell act as screening electrons, and then here are the valence shells. And again, in potassium, there are four shells. The electrons of the first three shells act as screening electrons, and then there is the valence shell. So the screening electrons reduce the attraction of the nucleus on the outer electron. So as the screening electrons are increasing, the attraction is decreasing, and the outer electron is getting further away from the nucleus. So it becomes easier to remove an electron, which is why down the group, ionization energy decreases. Now, in a period, we have to deal with nuclear charge to understand how the ionization energy changes. For example, in the second period, we have lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. What is nuclear charge? Nuclear charge is the attraction of the nucleus to the outer electrons. And again, over here, screening electrons decrease the nuclear charge. In lithium, there are total three protons, sorry, and there is one valence electron. So that means that apart from the valence electrons, there are two electrons which are in the inner shells. Those are called the screening electrons. So what are screening electrons? Screening electrons are the electrons that are in the inner shells except for the outermost shell or the valence shell. So in lithium, there are two screening electrons. So the nuclear charge is 1 plus 1. In beryllium, there are 4 protons, and again, two inner electrons or two screening electrons. So the nuclear charge is plus 2. And so down the group, the nuclear charge will keep increasing. 5 minus 2, this is plus 3. And so on for fluorine is 9 minus 2. So this is plus 7. Now, since the nuclear charge is increasing, the number of screening electrons are constant. So the attraction of the nucleus to the valence electrons is getting stronger, which is why across the period, ionization energy increases. Also, if we want to show this diagrammatically, so across the period, this is lithium, then beryllium, the atomic radius will be decreasing. This is because, again, the nuclear charge is increasing, screening electrons are the same. So outer electrons are being pulled towards the nucleus. So that's why the atomic radius decreases and it becomes difficult to remove the electrons, which is why the ionization energy increases across the period. So I'll do this once again. In the group, ionization energy decreases because as we go down the group, the number of screening electrons is increasing and the nuclear charge is increasing. However, and since the screening electrons are increasing, there are more shells. So the attraction of the nucleus to the outermost shell, to the outermost electrons, is getting weaker. which is why it becomes easier to remove the electrons. However, in the period, as you go as you go across the period, the number of screening electrons is the same. However, the number of protons is increasing, so the attraction of the nucleus to the valence electrons is increasing, which is why the valence shell is pulled inwards, which gives us this kind of a trend that the atomic radius decreases over here, which is why as the atomic radius is decreasing, so across the period, like fluorine will have a smaller radius, electrons will be closer to the nucleus. So in fluorine, it will be more difficult to remove an electron, while in lithium, electrons will be further away from the nucleus, and it will be easier to remove an electron. Next are the factors affecting ionization energy. The first factor is the nature of the orbital from which electron is to be removed. So in the first period, we have lithium, then beryllium, and then boron. So if we do the electronic configuration for beryllium and for boron, for beryllium, it will be 1s2 and 2s2. While for boron, it will be 1s2, 2s2, and 2p1. Now we can see that in beryllium, the electron that has to be lost is from the inner orbital, while that is the 2s orbital, while in boron, it's from the 2p orbital. So as in beryllium, as in boron, the orbital is further away from the nucleus. So in boron, the ionization energy of boron will be slightly lower than beryllium, because for in boron, it will be easier to remove an electron. So when we draw the graph of ionization energy changing in a period, there will be a dip between beryllium and boron. You'll see that in a while. Now, the next factor is spin-spin repulsion. For this, we'll take the example of nitrogen and oxygen. Now, we'll do the spin repulsion for both of these. Okay, so this is the configuration for nitrogen and oxygen. Now, in oxygen, in the 2p orbital, there is a paired electron. So when energy is provided to these atoms, what happens is that this downward spin, it absorbs that energy and it is transformed to an upward spin because of that gain in energy. This is what we did in excited state. We learned when we were doing ground state and excited state in the previous video, we learned that when energy is provided, the downward spin turns to an upward spin. Now, when there are two upward spins in this 2p shell in the first orbital, 2px, so what happens is that these two upward spins, they experience repulsion, which is why it becomes easier for oxygen to lose one of these electrons to because of that repulsion. So again, when we draw the graph of ionization energies across the period, there will be a dip from nitrogen to oxygen, because for oxygen, it is easier to lose an electron because of this spin-spin repulsion. Next is the half-filled and full-filled orbital concept. So over here again, we'll take the example of nitrogen and oxygen. For nitrogen, the configuration is 1s2, 2s2, and 2p3. And for oxygen, it is 1s2, 2s2, and 2p4. So what we know is that if an atom has half-filled or full-filled orbitals, then it is more stable than an atom that does not have half-filled or full-filled orbitals. So over here, nitrogen has half-filled, has 1s and 2s full-filled, and 2p is half-filled, whereas in oxygen, 1s and 2s are full-filled, but 2p is not half-filled. So nitrogen is more stable than oxygen. So for nitrogen, it is more difficult to lose an electron, which is why oxygen loses electrons more easily. So again, when we draw the graph, there will be a dip from nitrogen to oxygen because oxygen will have a lower ionization energy. Now, the fourth and last factor is the screening effect or the shielding effect. Screening effect or shielding effect is comes in effect in the groups. So for example, in the first group, the screening effect is the effect of the inner electrons that decreases the force of attraction exerted by the nucleus. So in the first group, we have lithium, sodium, and potassium. In lithium, sodium, and potassium, the configuration is 1s for lithium, 1s2, and then 2s1. So the first shell has 2 electrons, and the second shell has 1 electron. In sodium, it is 1s2, 2s2, 2p6, and 3s1. So the first shell has 2 electrons, second shell has 8 electrons, and third shell has 1 electron. In potassium, the first shell has 2 electrons, second shell has 8 electrons, third shell has 8 electrons, and the fourth shell has 1 electron. So we can see over here that in lithium, there is in lithium, there are 2 screening electrons. In sodium, there are 10 screening electrons, and in potassium, there are 18 screening electrons. Also, in these 3 atoms, lithium has 3 protons, sodium has 11 protons, and potassium has 19 protons. So the difference in the screening electrons and the number of protons is 3 minus 2, that is 1. Here it's 11 minus 10, that is again 1. And here 19 minus 18, that is again 1. So in these 3, in the group, down the group, the nuclear charge, the difference between the number of protons and the number of inner electrons, the screening electrons, is the nuclear charge. So since the nuclear charge is remaining the same, so shielding effect, nuclear charge is the same. So over here, the ionization energy decreases down the group because the outermost electron is furthest away from the nucleus in potassium, and in lithium is closer. However, if we went towards the periods, in periods, as we did earlier, the nuclear charge is increasing because the inner electrons are the same, but the number of protons is increasing. So we did for earlier, we did for lithium, then for beryllium, boron, and further onwards. So for lithium, there are 2 inner electrons and 3 outer electrons. So 3 minus 2, that is +1. For beryllium, there are 4 protons and 2 inner electrons. So 2 and then 3. Now in the period, the number of spinning electrons are remaining the same while the number of protons is increasing. So over here, the nuclear charge is increasing, which is why the attraction of the nucleus to the outer electron increases and the valence shell is pulled closer and it becomes more difficult to remove the electrons. So now if we draw the graph for the change in ionization energy across a period, we have atomic number on the x-axis and we have the log of ionization energy 1 on the y-axis. Again, we take the log because ionization energy values can be very high going across as they increase. So we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. From lithium to beryllium, it increases, but boron, because as we did earlier, over here, we saw that in boron, the orbital from which electron has to be lost is further away from the nucleus. So for boron, the ionization energy decreases. There is a small dip. Then for carbon and nitrogen, it increases. And again, at oxygen, there's a small dip. This dip is because of the spin-spin repulsion and because of the half-filled, full-filled orbital concept. Then again, after oxygen, fluorine, and for fluorine and neon, the ionization energy increases. And always the group 8 elements have the highest ionization energy in a period. And the one before so if we get a graph and we have to determine that which element is which, and over here the x-axis was not labeled, so we would see that the element with the highest ionization energy would be a group 8 element. The one before that, sorry, group 18 element. The one before that would be group 16 and the 17, and the one after that would be the group 1 element. So again, the highest one is group 18. Before that is group 17. After that is group 1. Now we'll go in detail in the subatomic particles. So there are proton, neutrons, and electrons. Protons have a mass of approximately 1 AMU, atomic mass unit. And so our neutrons also have a mass of 1 AMU, whereas electrons have a mass of 1 upon 1840. 1 upon 1840 atomic mass unit. So that's a nearly negligible mass. Atomic number or proton number are the number of protons or electrons in an atom, while mass number or nucleon number is the sum of protons and neutrons in an atom. And we can find the number of protons by subtracting the atomic number from the mass number. The deflection of subatomic particles in an electric field Protons are positively charged, so they are attracted towards a negative plate that is shown over here. And electrons are attracted towards a positive plate. Neutrons are neutral, so they are not deflected. Now the angle by which a proton is deflected and an electron is deflected. So the angle by which the electron is deflected, I'm supposing A, and for proton, I'm supposing B. So A will always be greater than B because protons have a smaller mass, so they are deflected more than, sorry, electrons have a smaller mass, so they are deflected more than protons. Now, how do we determine the angle of deflection? For that, we use the charge to mass ratio. So if we have a question in which we are given that a proton is deflected by plus 15 degrees and a particle Y is deflected by minus 5 degrees. And then we are given 2 or 3 different particles and we have to determine which one will be particle Y. These are protons, neutrons, and electrons. 1 and 2. So now we have to find which particle from 1 or 2 is particle Y. So first we'll find the charge to mass ratio for particle 1. Particle 1, charge to mass, for charge to mass ratio, charge will be 1 minus 2 because proton has a positive charge. So 1 for proton and then minus 2 for the electron. Upon mass, mass will be 1 plus 2, that is 1 for proton and 2 for neutron because electrons have a negligible mass. So 1 plus 2. So the ratio is coming, for particle 1, the ratio is coming minus, this is 2. So minus 1 upon 3. Now for particle 2, the ratio we'll have 4 charge plus 4 charge of proton minus 1 charge of electron upon 4 charge mass of proton plus 5 mass of neutron equals to 3 upon 9, that is 1 upon 3. Now these are the ratios for particle 1 and particle 2. Now we'll find the ratio of the proton and then compare it with these two particles. So for proton, the ratio would be plus 1 as charge upon 1 as mass. So the ratio is 1. Now 1 represents 15 degrees. This represents 15 degrees as we were given the question that the proton reflected by 15 degrees. So 1 is for 15. Now first taking particle 2. Particle 2 is 1 upon 3. So 1 upon 3 will represent x. Now if we find x, x will be equals to plus 5 degrees. Now if we take particle 1, minus 1 upon 3 is x. So if we find x, we'll get x as minus 5 degrees. So that means that particle 1 is particle Y. Once again, reviewing what we did over here. Proton was deflected by 15 degrees. We found the charge to mass ratio of proton, that was 1 upon 1. So 1. So 1 represents 15 degrees. Now we found the charge to mass ratios for particle 1 and particle 2. For particle 1, it was -1/3. For particle 2, it was 1/3. Now we made another ratio, and then using the unitary method, we found the deflection of particle 1 and particle 2. For particle 1, for particle 2, the deflection came as +5 degrees. For particle 1, the deflection came as -5 degrees. The given particle y had a deflection of -5 degrees, and particle 1 was getting a deflection of -5 degrees. So particle 1 is our answer.